I'm Kyung-Ju from Korea University, and I'm really happy to be here today present our work, which is entitled Fingerprinting Your Car Key to Prevent Keyless Entry Car Theft. This is a joint work with my colleague Won-seok and my advisor Dong-un Lee. In this talk, I will first introduce the keyless entry systems and highlight some security issues. Next, I will introduce our attack model and our method that we designed for the purpose of this research. Finally, I will present our evaluation results and discussions before summarizing our work. As many people already know, keyless entry systems have been developed and installed in modern vehicles for the convenience of drivers. Traditionally, however, it was necessary to physically insert a key into the keyhole to unlock the doors. This traditional way was inconvenient as well as vulnerable to the key copying, which leads to relatively easy car theft or break-ins. Therefore, car manufacturers introduced the keyless entry system, which enables a driver to unlock doors without inserting anything. The remote keyless entry system unlocks doors with the press of a button on a remote key fob at a distance. In the PKES system, car doors are automatically unlocked as the user makes physical contact with the door when the key fob is in the vicinity. Of course, wireless packets in these systems are encrypted and using pre-shared secret key and rolling code system. Despite these security mechanisms, several vulnerabilities with keyless entry system have been discovered. Especially in 2011, researchers demonstrate a relay attack on PKES system, which is practical enough to use in real car thefts. More recently, in Germany and the United Kingdom, thieves successfully carried out this type of signal relaying attack, which were captured on security cameras. One approach to resolve these issues might be the use of an RF distance bounding protocol. However, since the distance bounding protocol measures the distance based on the time of flight of an RF signal, this system is highly sensitive to timing errors. Recently, an ultra-wideband-based radio ranging technique has emerged as a prominent technology to deploy a distance bounding protocol, and numerous efforts are underway. However, this approach would require an entirely new keyless entry system. To detect attacks, we employed an RF-fingerprinting technique that extracts fingerprints of individual key fobs from the RF signal. Due to the imperfection of hardware imperfection and channel environments, by analyzing RF signal in physical layer, distinct features per key fob can be extracted even if they transmit the same binary message. The detailed contributions of our work are as follows. First, based on previous attack demonstrations, we present a new attack model that combines all known attack methods. Also, we present an RF fingerprinting method which implies that the current system would require no alteration. Finally, we evaluate under varying environmental factors. Next, I will describe some background knowledge, especially about PKES system. Vehicle periodically broadcast RF band signals to check if a proper key fob is in the vicinity, like beacon signals. When the key fob is within the communication range of an RF band signal, the vehicle and the key fobs are communicate following predefined communication protocol. In our case, since the vehicle should verify the signals from the key fob, detection module should be equipped with an RF receiver and integrated with the body control module. When an attack being detected, our detection module raises an alarm, and BCM does not transmit the unlock command through the in-vehicle network. Next is our attack model. The first attack type in our attack model is a single-band relay attack. The PKE system was originally intended to only operate within the RF band communication range, which is 1 to 2 meters. However, by relaying an RF band request from a vehicle to its key fob, an attacker can trigger the key fob even if it is out of the RF band communication range. In addition, this RF band signal can be relayed by either wire or wireless communications. Then, the response from the key fob is directly transmitted to the vehicle. Since the communication range of UH band signal is almost 100 meters, attacker no needs to relay this signal. Unlike single-band relay attack, a dual-band relay attacker manipulates both RF band and UHF band signals. I will first demonstrate an amplification attack in which the attacker injects UHF band signals using a single signal extending module. During an amplification attack, attacker simply amplifies both RF band and UHF band signals using an RF amplifier. In a digital relay attack, attacker performs the whole process of digital communication to inject attack signals. Attackers demodulate both RF band and UHF band signal to forward binary information to each other. After receiving the binary information, the attacker injects an attack signal through a modulation process. Finally, we defined another type of attacks on PKE system except relay attack. In a cryptographic attack, the attacker exploits the weakness of cryptographic algorithms which is equipped in the PKE system. After collecting sufficient challenge and response pair, the attacker performs cryptanalysis to extract a long-term secret key. In terms of our method, this attack scenario is considered to be the same as the digital relay attack. This is because attacker injects attack signal using valid binary information. Next, I will explain our design decision to realize our method. There are two main phases in our method, the training phase and the attack detection phase. In training phase, we create a classifier based on a training data set that contains only legitimate signals. In attack detection phase, based on the normalized output of classifier, we make a decision whether the received signal has been transmitted from a legitimate key fob or not. I will demonstrate the detailed procedure in the following slides. In pre-processing, to obtain a meaningful information, we first remove the carriers and noise signals. After the demodulation process, the signal is normalized to scale its power to a certain value. In addition, I would like to denote that we extract the features from a preamble region which has a static value independent to the payload data. Next, we first extract the features from the frequency domain of preamble signal. As you can see in the below figure, there are several dominant peaks exist in the frequency domain. Since the peak frequency represents the period of preamble signal, it represents the bit time characteristics of a key fob. We extract more features from both time and frequency domain. Before introducing employed feature set, I would like to denote that these listed features are the result of exhaustive feature selection by limiting the number to 5. Feature selection is essential procedure since we can minimize the execution time and overfitting problem. You can see the full list of statistical features in reference of our paper. First, signal to noise ratio represents the difference between the baseband signal and the noise level. Kurtosis is a measure of peakness of the sampled signal in the time domain. Spectral brightness represents the signal power in the high frequency domain. Finally, carrier frequency offset represents the difference between the actual and ideal carrier frequency. Before the attack detection, we first train our detection module only using legitimate signals, utilizing semi-supervised learning. This is because the feature extraction during training can only occur using the legitimate key fobs. Inspired by the K-fold cross-validation, we randomly select 90% of the legitimate data set for training and 10% of data set for testing. After repeating 10 times to accumulate the output of the test data, we calculate the mean and standard deviation of corresponding key fob to normalize the output from a newly received signal. In the attack detection phase, features are extracted from the newly received signals and the corresponding classifier's output is normalized. If the normalized output is within the threshold, we consider the signal as legitimate. In contrast, if the output from the classifier exceeds threshold, the corresponding signal is considered as malicious. In evaluation, we performed a series of experiments on actual vehicles from Kia and Volkswagen. HEC RF was used to sample the signal from the key fob, and the other HEC RF coupled with the USRP used for injecting attack signal. With GNU radio, we can control the SDR device as an UHF band transceiver with the sample rate of 5 megasamples per second. In addition, loop antennas were used to relay RF band signals from the vehicle. Due to the limited time, I'll present our evaluation results focused on Kia. Experimental results on Volkswagen can be found in our paper. Next, we employed a one-class support vector machine and KNN algorithm for training and attack detection. In addition, our evaluation results are focused on the false positive rate while assuming the 0% of false negative rate. To simulate the single-band relay attack, we relay the RF band signal to trigger a key fob at a distance while varying the distance. Of course, in every trial, we confirm that the vehicle verifies the attack signal as legitimate. In every distance, both algorithms can easily differentiate the attack signals. Intuitively, as the distance increased, it became more easier to detect a single-band relay attack. In an amplification attack, we used RF amplifiers with analog bandpass filter to amplify signals from the key fob. During the simulation, we set the distance between the attacker and the vehicle to the point where the SNR level is equal to that of legitimate signal. This is because when the attacker injects the attack signal with the higher SNR than the legitimate case, we can easily detect an amplification attack. In results, we found that this distance was between 20 and 25 meters. As seen in figure, even if the distance between the key fob and vehicle is greater than the maximum distance of a single-band relay attack, the normalized output is much closer to the legitimate case. Nevertheless, both algorithms can effectively differentiate the attack signals in our results. In digital relay attack and cryptographic attack, we simulate attack signals using SDR devices. Using valid binary information, we inject the attack signal following a specification of keyless entry system. In addition to the SDR devices, we further extended the capability of digital relay attacker. We assumed the strongest attacker who can access to the identical electronic component as the target key fob. For example, if the number one key fob was to be chosen as legitimate, features from the other key fob would be assumed as an attack. Especially in our results, features from the number 3 key fob are closer to that of number 1 key fob than the other devices. This is because the 2 key fobs were manufactured in the same year and month. However, both algorithms produce a very low average false positive rate. This is because the key fob has a distinct bit time characteristics due to the hardware clock imperfection. Next, we also assume the environmental factors that can be occurred in practical scenarios. In this evaluation, different from the previous attack detection, we should verify the legitimate key fob in the different channel condition. First, we sample the signals from the key fob that placed in the pocket or backpack. In result, we observed that both algorithms maintain the performance. Next, we further evaluate our method under dynamic channel conditions, such as an underground parking lot and roadside parking space. In this result, we observed that the relatively high false positive rate in underground parking space. This is because we think that the interference due to the modified components affected by such as ceiling and concrete pillars. Next, we also assume the temperature variation and battery aging. In this case, we use the RK system signals to evaluate this attack detection performance. In results, both algorithms can maintain the performance in both cases. We also measure the total execution time in our method based on Python and Raspberry Pi implementation. It took around 160 milliseconds to verify the newly received signals, We finally evaluate the feature importance as a function of each attack scenario. Based on the relief algorithm, we rank the features in each attack detection experiment. Table shows the rank of features as a function of attack detection scenario. So this is the discussion and conclusions of our paper. First, in our design, the security level highly depends on the threshold. Since the threshold is a trade-off parameter, it should be determined carefully. Next, feature impersonation is a real threat to our detection method. Through the series of experiments, in some attack scenarios, attackers could successfully impersonate some features. However, to bypass our method, attacker must impersonate the whole feature set at the same time. We observed that impersonating a specific feature leads to a distortion in other features. In case of practicality, it is required more shortened execution time to maintain the convenience of the drivers. In this paper, we present a sub-authentication system that supports current system to prevent keyless entry car theft. Through our evaluations, we show that our method can effectively detect simulated attacks while reducing the number of erroneous detections. Furthermore, we found the set of suitable features in a number of environmental conditions that makes it possible for our method to properly operate in real-life environment. So this is our talk. Thank you for your attention. I'll be happy to take any questions.
Well, to get us started, I think you hinted at this a little bit towards the discussion, but can you talk a little bit more about what makes it hard for someone to do the same learning and fingerprinting that you do and replicating those fingerprints?
The important factor for replicating
so an attacker was going to just take your methodology and try to replicate the fingerprints.
Yeah, attackers should their best effort to impersonate whole feature set to bypass our method. So we try to show that our method can detect some strong attacker like amplification attack with bandpass filter, and I will show some this result. In this attack scenario, we also assume the attacker can directly recall the signals from the key fob and directly play back it to the inject for attack. So we sample the signals from the key fob in various sample rates, but we observe that it is still effective to detect such attacks, like using 100 megasamples per second sample rate and other sample rate in various, yeah.
Any other questions? If not, let's take the speaker again.